So we're looking at page 68 in the Unit 3 packet. Testing a claim about two means, specifically in case of independent samples. The assumptions that we're dealing with independent samples and that both samples are sufficiently large and that they're simple random. You start to kind of get to a point where you can go a little bit quicker with some of these tests because there's a lot of similarity from one test to another. So you see in the step one, the excuse me, mu1 equals mu2 versus greater than, less than, not equal, and their counterparts set equal to 0. Those are consistent with what it was like for the matched pairs situation. Alpha, p-values, conclusion, that's all the same, or same structurally. And then in terms of the calculator approach, what we're saying is that it's a t distribution. All right, so specifically a t-test. All right, so let's dive into an example. Great Buy and Circuit Town both claim that they offer the best prices. A sample of 50 randomly selected items from the inventory of Great Buy. So let's start kind of denoting this. Great Buy, 50 items, that's an N of 50, was collected. The mean cost of the items was $97.50, so X bar 97.50 with a standard deviation of 1719. All right, then we have Circuit Town. 32 items were selected from there. The mean 76.59, and the standard deviation for that sample $12.63. Using a 0.05 significance level, so I'll just jot that in over here. Test the claim that there's no significant difference. No difference means equals. So that means my first population would have to have a mean that's equal to my second population, because I have two populations. It's just a question of which one is the first one and which one is the second one. Well, that's up to you. So what I'll say is, first comes first, second comes second. So Great Buy gets subscripts of 1, Circuit Town gets subscripts of 2. All right, so this distribution is a t distribution. So we can go to our t-test calculator. All right, so we can start toggling things the way they ought to be. The test statistics is going to be an interesting one because we'll have to kind of make a slight adjustment or massive adjustment depending on how you look at things. But we'll cross that bridge in a sec. So first, let's start off with the 0.05. Now, they said test the claim that there's no significant difference. The alternative to that would be that there is some significant difference, which is a two-tailed situation. All right, so we're going to get our critical values from the calculator, 0.05. But we need degrees of freedom, but the question becomes, well, which one of these n values are we going to use for degrees of freedom? The answer to that is the smaller one. Ooh, I don't know what I just did there. I know what I did there. I accidentally grabbed the image file. All right, so degrees of freedom is the smaller of n1 minus 1 and n2 minus 1. So in this case, we're talking about 32 minus 1, which would be 31. All right, so the sample size I would use would be the 32. We'd use that as the n in our calculator. All right, my slider only goes up to 30, so let me just tap onto that and make it a 32. All right, you'll notice that only one side is shaded in. That has to do with the fact that I just used this calculator for a different problem and I left the setting on, so let's not worry about that just yet. Degrees of freedom, 31. critical values. So it's two-tailed. So not left-tailed, not right-tailed, two-tailed. On the left side and on the right side, we're looking at negative 2.0395 versus positive 2.0395. Okay, so that corresponds with a 0.025 on either side, which in total gives us that 0.05. All right, so now we need our test statistics. So this is where it gets interesting. So the test statistic for a two-tailed, well, not two-tailed, sorry, a two population proportion test for independent samples. And I said proportion, I meant to say mean, two population mean test for independent samples, apologies. You're going to be x bar 1 minus x bar 2 minus mu 1 minus mu 2. Now that's an assumed value, so that corresponds with the null hypothesis. So that's actually going to go to 0, so you don't really have to worry about that. Over the square root of S1 squared over N1 plus S2 squared over N2. So that's what we have to compute. So we just have to run these numbers. Easier said than done, but doable. Now you'll see here, you know, we have these critical values. We can get our critical regions going. You know, it's, I don't want left-tailed, I want two-tailed, so I turn those both on. That looks great. You get down to statistics and then you say, oh, wait a minute. We got a problem here, Houston. It just says X bar. It doesn't say X bar 1, X bar 2. I mean, we could modify this to make that happen, but we'll be spinning our wheels a lot, so that's not going to be good. The parameter we can make a 0. That's easy enough. All right, mu sub O, we'll call that 0. If it'll sit on that. Nah, it doesn't seem to want to, so I might have to type it in a sec. Okay, it actually worked at the 11th hour. All right, but that test statistic, I mean, it's the incorrect test statistic. So this is where our calculator kind of breaks down and we have to do the computation by hand. Right? So what we would do here is actually get rid of this and just put it in manually. All right? X bar 1, 97.5 minus X bar 2, 76.59 over the square root of fraction 17.19 squared over N1, which is 50, plus another fraction, 12.63 squared over N2, which is 32. All right, so we have our test statistic now, which is approximately 6.335. All right, so that's actually pretty huge in comparison to the critical values. I mean, again, if we assume that negative infinity is out this way, positive infinity is out this way, 0's in the middle. If I'm trying to plot 6.335, it's going to be way over in the shaded region over here somewhere. All right, so it's going to cause a rejection of the null hypothesis, but just to really pin it down, what we would do is compute the p-value, which is the probability that t is greater than 6.335. So we can actually, now that we made that adjustment in the test statistic, we can go into our p-value calculator and its two-tailed distribution. We can go down to that value and it's going to be correct because it's based off of the t-value that we just put in. And so 4.74, 4.748 or 4.75, either way. I'll say 748 times 10 to the negative 7th power, which is a teensy tiny minuscule little number, way smaller than 0.05. That's going to tell us to reject the null hypothesis. So the null is out, the alternative is good to go. Since the first sentence in our conclusion addresses the null, I would say that there is sufficient evidence to reject the null. Now that null in words, it's that there is no difference, no significant difference between the average cost between these two stores. So there is sufficient evidence to reject the claim that there is no significant difference between the average cost at Great Buy and Circuit Town at the 0.05 significance level. Now, since that happens to be what the question was asking, we don't need any other statement. So all this stuff is gone, not required. It's part of the template, so I have it there because you might need it in some cases, but it turns out we don't need it in this case. Now, you'll see here that I didn't use the word population in the conclusion. You can go either way with that in this particular case, only because the way the question was phrased, it says no difference, no significant difference between the average cost of items at Great Buy and Circuit Town. Okay. So we stole their phrasing so we can get away with it, but typically we want to have the word population in there.